ME350 example problem for steady, one-dimensional conduction with heat generation. A plane wall of given thickness and thermal conductivity having a uniform volumetric heat generation is insulated on one side while the other is exposed to a fluid with a specified temperature and convection heat transfer coefficient, as shown. For part A, sketch the temperature and heat flux distribution in the wall. For part B, determine the maximum temperature in the wall and the heat flux distribution. Our first assumption for this problem is steady state, which means that none of the properties are changing with time. Our second assumption is one-dimensional conduction in the x direction only, which is based on the information provided in the problem statement. Our third assumption is constant properties, which is reasonable as long as the properties have less than a 10% variation over the range of conditions. Our fourth assumption is that the heat is being generated uniformly in the wall. Our fifth assumption is perfect insulation on the interior boundary, which corresponds to negligible heat transfer and a temperature gradient of 0. Our sixth assumption for this problem is negligible radiation for the exterior boundary. This is a reasonable assumption for an opaque wall and for moderate temperatures combined with significant convection at the exterior boundary. For part A, we want to sketch the temperature and heat flux distribution in the wall. First, we draw our x-axis from 0 to L. Second, we draw our temperature axis and indicate the limiting temperature of 92 degrees Celsius in the fluid away from the surface at x equals L. Next, we know that for zero heat flux at x equals 0, the temperature distribution must start out as flat. We also know that for uniform internal heat generation in a plane wall, the temperature distribution is parabolic. Finally, we know that the temperatures in the wall must be higher than that of the surrounding fluid. Thus, we infer that the maximum temperature will be at x equals 0, and then it will decrease parabolically with x to T sub s at the surface where x equals L. The magnitude of T sub s must be between the maximum temperature and the fluid temperature by the second law of thermodynamics. Finally, we add a curve to the temperature distribution as x increases further to indicate that it decreases rapidly from T sub s to the fluid temperature. We will discuss later in the course why this is correct when we cover convection. For the heat flux distribution, we begin by drawing an axis on the right for heat flux and indicate that the heat flux is 0 at x equals 0 as specified. Next, we know that for uniform internal heat generation in a plane wall, the heat flux distribution is linear and will increase with x. Finally, from an energy balance on the entire wall, we know that the heat flux at the outer surface is equal to the rate of energy generation in the wall times the thickness. For part B, to determine the maximum temperature at x equals 0, we begin by writing the heat diffusion equation, which is a form of conservation of energy for conduction, as a partial differential equation, or PDF, in vector notation. Next, we expand the first term using the definition of the gradient and then the divergence for Cartesian coordinates. For this problem, we can reduce this equation by assuming steady state one-dimensional conduction in the x direction and constant properties as shown. Note that we can now write this as an ordinary differential equation, or ODE. To solve for the temperature distribution, we integrate twice with respect to x to get a parabolic distribution as expected with two constants of integration. To determine these constants, we need to apply our two boundary conditions. First, for the boundary at x equals 0 with 0 heat flux, which corresponds to 0 temperature gradient, we get that C sub 1 is equal to 0. Second, for the boundary condition at x equals L with specified convection only, We use the boundary condition developed in example 1 from an energy balance at the surface at x equals L. Substituting in our temperature distribution, we solve for C sub 2 as shown. Substituting in our constants, we get our final equation for the parabolic temperature distribution. To verify that the maximum temperature is at x equals 0, we take the derivative with respect to x and solve for when it equals 0 to find that the only inflection point is at x equals 0. Then we verify that this location is a maximum by taking the second derivative with respect to x and showing that it is always negative. Thus, the entire temperature distribution is concave downward, and x equals 0 is a maximum. To get an equation for the maximum temperature, we substitute in x equal to 0. Finally, we calculate the value to be 212 degrees Celsius, which is significantly higher than the surrounding fluid. Continuing with Part B, to determine the heat transfer rate per unit area or heat flux, we use Fourier's law, the rate equation for conduction, for just the x direction for our one-dimensional problem. Substituting in our known temperature distribution, we solve for the heat flux distribution, which is linear as expected, for this case where the temperature distribution is parabolic. Also, we verify that the heat flux at the surface at x equals L is the same as that indicated on our sketch for Part A, which we inferred from an overall energy balance on the wall. Finally, we note that an alternative method for solving Part B is to use the solutions provided in Appendix C of our textbook for steady one-dimensional conduction with internal heat generation. Using Table C.3, we can look up the temperature distribution for a plane wall with one insulated boundary in terms of the surface temperature at x equals L. Then we can use Table C.4 to account for the convection to the fluid by finding T sub s in terms of the convection parameters. These results for the temperature and heat flux distributions are the same as those found earlier. Finally, note that Appendix C also has results for cylindrical and spherical geometries. When using these tables, make sure to ensure that the nomenclature, geometry, and boundary conditions in the table are consistent with the parameters for your problem.